Okay, so in this in this field of active control, one idea is to try to test the scheme that you want to implement using simulation. Instead of having a true experiment, you would have just a Navier-Stokes flow solver here, and you put a controller on that and return, you see, you make a loop like that, and you control this, what happens in the simulation itself. So that's, again, quite attractive, at least from a theoretical point of view. You think that if your Navier-Stokes solver represents reality, then you can test your ideas directly. That is, you implement the controller here, you test if it works and what it does, and then you can implement that experimentally. So we actually, at one point, we started working on the following problem. The rocket engines, solid propellant rocket engines of very large size contain baffles. You see the segment of propellant is separated by baffles, and behind the baffles there is vortex shedding because these baffles protrude in the flow. So you have vorticity which is shed from the baffles, and this vorticity hits the nozzle, and pressure waves are returned by this collision of vorticity with the nozzle, and this produces a pressure field here, and if the pressure field corresponds to one of the modes of this system, you can synchronize the shedding of the vorticity, and so this system can become synchronized. And it's very low frequency because these devices are big, so it's less than 20 hertz. It's pretty low frequency. It's not always, the level of oscillation is not very large, but you can show that it produces thrust oscillations, typically of the order of 1%. So the whole thing is shaking at a low frequency and with a thrust vibration of about 1%, 1 or 2%. So then this is not good for the payload. It's not good for the launcher. It's not good for the payload. So you are very careful about the comfort of your payload. You want it to be in the best possible acoustic, vibroacoustic field, the lowest level of oscillations and vibrations. So then the idea was to add to this solid propellant rocket an actuator which would inject a liquid, an oxidizer, in fact, because the atmosphere is reducing here. The gases still can burn, so if you inject an oxidizer here, you can have a source of heat release fluctuations, and you can counteract what goes on here using an adaptive technique and a sensor that would sense the oscillations here, return them into this adaptive controller and back into the actuator. So I had a very nice student, Manuel Mettenleiter, and also an American student who is now in France, Edward Hale, and we started working on this problem. Of course, you don't work on the device itself. It's too expensive and too difficult. So you start with a simple model scale system. So here is just to show what happens. You see the vorticity, which is here, hits the nozzle, returns pressure waves. You have other situations where the vorticity is shed from the solid propellant directly like this, and it is synchronized by the pressure waves. And there is another mechanism where vorticity is just shed from the boundary itself of the the solid propellant. So even without baffles, even without an edge, you do have organized vorticity which is being shed. And if this vorticity is clocked, synchronized by the pressure, then you have this mechanism which can take place. And you can actually see when does that mechanism become, let's say, important. So suppose this is the period, the acoustic period, and you have the number of vortices here. So the period is the acoustics in this big setup. It corresponds to the resonant frequencies of this device. And what you have here is that you have to do this, this distance at a certain convective velocity. So m times the number of vortices is here, the period is here, and here you have the time corresponding to convection of the vorticity to this nozzle to cover this length. Then you have an acoustic time to go back here, and it is much shorter, in fact. And then you have something which explains or which represents the delay between the convergence from convective to acoustic mode, for example, here. And when you consider that delta t is a fraction of t, you obtain this expression. So this gives you the conditions where you have this matching between the resonant frequency and the frequencies of these modes. So there you have this mechanism taking place. And so we did experiments to replicate something like that. You have a baffle here. Now we put a driver unit here. You have this nozzle. This was done at VKI with a gentleman called Antoine. And we brought our control algorithm, adaptive, and we placed a filter here. We had the low-pass filter here, and then the driver unit. And so the game is here. Now the system operates in a suction mode. So you see the fan is downstream. You have the nozzle here, and you have the fan which sucks the flow from the test section. And this is a plot of the frequency that is observed in the system as a function of velocity in this test section. And you see that certain frequencies appear at a strong level in decibels. You can have pretty high values at particular frequencies. Of course, the device is much smaller than the rocket, and so the frequency is multiplied by the scaling between the two. Typically, if you want to get back to the rocket, you have to divide these frequencies by, let's say, 20. The model is 1/20th version, idealized version of the rocket. And when you put the controller on, you see that you essentially suppress all these oscillations. So not only the first one, but essentially all. So there is a possibility to actually do that. Experimentally, we used it to look at the details of the flow and so on. It's in the paper in the Journal of Sound and Vibration. And then what you want to know is it possible to do that numerically? That is, you calculate the flow here. You take a signal somewhere from a pressure sensor, send it to the controller, and actuate right here to send pressure waves to counteract the pressure waves of this device. And then you have to be careful. This is described in the AIAA journal. You have to put sources in the equation of mass, balance of mass, but you also have to put sources in the equation of energy, because if you don't put this one, you miss something. This is quite important to actually have these two terms. Oh, I don't know. So there are a few difficulties in doing this exercise. You see, this is all simulation here. And some difficulties are the fact that your controller here operates at a very low frequency, for example, 20 kilohertz. You don't have to do control at a very high rate. But the computer, the calculation here, operates at a much higher frequency. The time step is much smaller because you need it from the fluid mechanics point of view. So what you have here is to bring these signals from here, and it's important that the signals are low-pass filtered so that they get, if you keep high frequencies coming from this and you send them at a low frequency here, you have a problem. So there is a low-pass filter to place here. If you don't put that, this sort of simulation doesn't work well. And then you put your control algorithm and you obtain a signal which is actually, it's not, it's discrete. It has discrete values. So again, if you don't put a filter and you send directly what comes out from the controller to this actuator, you put a lot of high frequencies, and these are not well handled by this calculation here because the viscosity is low. It's an LES type calculation. And so again, you need to place a low pass filter here. And why I'm saying this, because at first we didn't do that. We just took the signal, placed it here. This is the same controller as the one that was tested experimentally. It's the same, exactly the same. It's here you use a Navier-Stokes solver. Here you use your control, the adaptive control method, which requires some identification as well. And then you close that loop and you see what happens. And this is what happens. So basically, this mismatch rapidly deteriorates the simulation. The problem is suppressed by placing low-pass filters at the controller input and output. And you switch the controller on, and you see that you bring the level of pressure fluctuation to a lower level. It goes through all sorts of fluctuations. Why? This is the signal from the actuator. Once you are here, you see the signal is pretty low, and the level is much lower than what you had at the beginning. And this is what happens in terms of vorticity. This is the vorticity which produces a high level of pressure fluctuation. And then you fabricate something where you still shed vorticity. It's not possible to have such a flow, a shear flow, without vorticity. But here now the vorticity is different from that. It's at a lower level, and in addition, you have more vortices, and so the pressure fluctuation is reduced by the controller. It's, yeah.
Is that the vorticity there a factor of the fact you're limited in frequency response of the controller?
No, all that is very well resolved by the controller. This is 20 kilohertz control, while the processes here are, let's say, at it's a scaled version of the rocket, so that they are really in the band, no problem there. But if you are not careful about the signals that you take out, because the frequency of the controller is much lower, then you have a lot of aliasing taking place, so that's bad. So that's why you have a low-pass filter at the entrance. And the exhaust is also, does not give you an analog signal. So you need to low-pass filter what comes out. And when you do that, you have a demonstration of closed-loop active control, numerical, purely numerical, which is, there is a lot of discussion about things like that in the literature, very complicated methods. So here you have a translation of what you've done experimentally into the numerical framework. Okay, so that's for control. And so now we go to the dynamics of swirling flames. Up to here, we looked at rather simple flames. And here, we now want to go to something which is more practical. In many devices, you have swirling flames. This is still a laboratory scale swirling flame. You see the flame is sitting here. It's in a duct and made of quartz. And there is a laser beam shining here so that you can do laser Doppler velocimetry. This is another device where you have a swirling flame. You have here an injector, and it produces, this is also in our lab, you produce a swirling flame coming out from a tip very close to an industrial swirler. Now you see that the confinement is rather strong, and so the flame reaches the wall in this case. In many applications you have swirl. For example, in thermal power plants, combustion is stabilized with swirl. The swirl produces a central recirculation region. Suppose you have a swirler right here, and you exhaust gases. What happens is that you produce in this region a recirculation of hot gases. So these hot gases will ignite the flame. You don't want the flame to sit on the swirler, on the injector, but it's not far. In addition, usually this is placed in a backplane, and you have also regions of recirculation which develop on the sides. So you have a central recirculation zone, and you have also lateral recirculation zones, which are like that. So the principle of the swirling flows is to be able to stabilize the flame aerodynamically. You want the flame to be there all the time, and this is used in aircraft engines, this is used in gas turbines, is used in power plants. So the dynamics of these flames is a central issue in many applications. So you see this central recirculation zone is right here. This is a calculation of such swirling flames, and you see that this region here is the recirculation. Of course, these flames are turbulent. There are many dynamical issues. For example, this is an example of what waves, large-scale oscillations can produce. They break this metal sheet here. These swirling flames are rather compact as well. So that's another interesting feature, is that by using swirl, you have more compact flames, and like that, your combustor can be compact. In aircraft engines, it's very important because like that, the distance between the turbine and the compressor is smaller, and so it's less heavy. It's easier. Instead of having a long axis, you have a short axis. So having a compact combustor is nice. So what we want is to examine the interaction between the swirler and acoustic waves, determine effects of this interaction, and obtain the flame response in terms of describing function. Use the describing function in the analysis of generic systems comprising a single injector. So this is a typical swirling flame in confined. This is another one. This is the upstream manifold. We use the same burner, but now it is equipped with a swirling system. Now you can have axial swirlers. That is, devices which put the flow in rotation and which are just axial, but you can have also radial systems which actually induce this rotation, this rotational motion in a radial fashion. And very rapidly we started actually looking at the describing function of these flames. This is work done with Paul Paliès. And what we found is that the gain has this very special shape. You see, you start with something which is like 1, and then these are premixed, and then you decrease, and then you increase again, and finally it goes down, so it's low pass, and the phase has this special shape as well. So there is a maximum here, there is a minimum, so you have that here. And if you look at the dynamics of these flames, now in this case there was still a bluff body, but we did also studies without the bluff body. So it's a swirling flow with a bluff body. So at 60 Hertz, you have one kind of motion here. At 90 Hertz, here, you have a different kind of motion. So definitely there is something happening in this case. There is an interference which takes place. So the point is the following. Here, when you have a duct and you send acoustic waves, you know that what you have here is acoustic waves. You don't produce anything else in this case. But now you place a swirler, for example, this axial swirler, which you can describe theoretically like veins set at an angle. It's like a cascade of veins. And the question is, what do you produce on the downstream side? You have on the upstream side acoustic waves. What do you produce on the downstream side? So in fact, to look at such a problem, I always have a good reference. It's my Frank Marble. So yes.
What's the swirl number that you're using here?
So the swirl number is typically in our experiment 0.6, 0.7. So it's typical. It should not be too high. So the question is about the swirl number. This is an important quantity. It describes the ratio of the azimuthal momentum to the axial momentum. If you have it too low, it doesn't stabilize properly the flame. So you have a region where the swirl number is reasonable. It's typically 0.6, 0.7. Many studies are done without quoting the swirl number. Many studies are done by quoting the swirl number calculated from the geometry. That is, you know the geometry and you say the swirl number is so much. Very often what is quoted in terms of swirl number from the geometry doesn't correspond to the swirl number that is determined experimentally from the profiles. So the best way is to actually measure the profiles. So you have to measure the azimuthal component, the axial component, and calculate the swirl number using the standard expression, and you have the proper idea of the swirl number. But in some cases, you just put a swirler and you don't even know what is the swirl number. And so then the swirl number plays an important role here. Yeah.
One more question.
Yeah.
You did mention that there was a bluff body in the flow.
Yes.
Is that just the central body for the veins, or did you put a different bluff body intentionally over there?
No, we placed this central body because at first we thought we would have a hard time stabilizing purely aerodynamically. But afterwards we found that it was quite possible, was not, so it's true that this case is, the initial studies were done with a rod in the center, but it's not required, and we did later studies with just radial swell numbers. There is a paper in CST where we compare actually the two. They have the same features. You find the same features. What I've shown here is typical of such flames. And why is it typical of such flames? Is because of this, this device. When you place this device in the flow and you give swirl, what you produce on the downstream side is an acoustic wave, which is transmitted across the cascade. But what do you produce in addition? What can you expect in addition to the acoustic wave due to this presence of the cascade? A vorticity wave. You produce a vorticity wave and now the question is, of course you have the notes and maybe you've seen that in the notes, but if you said it like that, it's good. I didn't know that. I didn't, when we started, we didn't think about that. We just placed the swirler and that was it. But afterwards, so I go back and what you really want is to evaluate this idea. And I remember that Frank and Nick Comsty in Cambridge did a very nice piece of work where they study the entropy wave entering a blade row and producing pressure waves. It's a continuation of this idea of entropy waves interacting with nozzles produce pressure waves. Here, entropy waves coming from combustion get into the blade row, which is the turbine, and they can produce a pressure wave here. And so they worked out the expressions, so you can take a look at that paper. It's the Proceedings of the Royal Society. Frank, while I was doing my military service in France, I was in the tanks, he was in Cambridge on a sabbatical year. So he worked with Nick Comsty at that time. So, taking their theory, it is possible to actually use what is called the how's that? Yeah, I forgot the name. Anyway, you use their theory, and what you find is that on the upstream side, you have some reflection. So in fact here, this cascade reflects the wave, but the reflection coefficient is rather low. And on the downstream side, you have an acoustic wave, which is just this one, like the standard waves. You see, you recognize a wave which propagates in the downstream direction. But in addition, you have a convective wave, which is this one. You see the... Otherwise, you cannot satisfy the equations describing the cascade. You cannot, if you just consider that you have purely acoustic waves, you do not satisfy these equations. So you have the cascade here. And on this downstream side, you have U'2, and you have also a wave, and this wave corresponds to velocity fluctuations in the transverse direction, V'2. And this is a convective wave, B exponential. It has the same frequency, minus I omega t, as the acoustic wave. You see this one is A times exponential of I x over c minus I omega t. And there is an omega here. And this one has I omega x over the flow velocity, which I called here U2 bar. And this is required. If you don't set the problem like that, you cannot satisfy the matching conditions in the actuator disk theory. This is the thing that I forgot for a little while. You consider that as an actuator disk. And so there is a theory for these actuator disks it's a theory, an unsteady theory. What happens to a wave getting into this actuator disk? So I just took the equations from Frank Marble and Nick Comsty. And the point is to know what is B. What is the amount of B that you need here? Is it small or is it big? And what you find is that it's equal to A over rho 0 C. So in fact, U prime 2 is also divided by rho 0 C. Rho C. It's the velocity. So you have the impedance here. But, and you see that B is A over rho 0 C tangent of theta 2, and theta 2 is just the angle of the blades at that point, at the edge, at the trailing edge of this cascade. So you can write down this expression, and you see these amplitudes are about the same. Tangent of theta 2 is like 1, and so you have something which, so the vorticity wave is as strong as the acoustic wave. And of course you can say, is it really true? So we calculated this situation. You put a blade row here, you send acoustic waves on the blade row, and you look at the velocity on the downstream side, and you see that U prime 2 is here, and V prime 2 is here. So definitely you produce a vorticity wave on the downstream side, and V prime 2 is equal to U prime 2 tangent of theta 2. Theta 2 was 25 degrees here. So, and this is at 60 hertz. We did it at 100 hertz. This is Paul Paliès did the calculation here. And because we were not persuaded that all that was true, we also did an experiment where you have a loudspeaker, you put the swirler, there was a rod in this case here, and then you look using laser Doppler. You can actually look at the axial and azimuthal direction. So this is axisymmetric. So you can actually measure. So in this case, V prime 2 is the azimuthal fluctuation, and U prime 2 is the axial fluctuation. And what you find is that U prime, the phase between 2 points is essentially constant, because this is acoustic. So the time delay is very short, and so for the acoustic wave, U prime is essentially like that. But for the V prime component, you are convective, and the convection velocity is just the velocity in the duct. And you can see that, and of course the phase increases. You see the phase is directly proportional to the frequency, 2 pi f tau. And so you have this sort of convective mode. So you have a combination of an acoustic mode and a convective mode. And like that, you know now that the flame will respond to these two perturbations, not only to the acoustics, but also to this transverse convective mode. And so mode conversion at the swirler generates an actual acoustic wave and an azimuthal velocity fluctuation in the 3D case, or a transverse velocity fluctuation in the 2D case, a convective vorticity mode. And this has important consequences on the flame dynamics. And so this is the device. So you see it's cooled. You have the burner here. This is the flame sitting here. You have this confinement. Initially, we had this rod, but afterwards we used radial swirlers, and we didn't have the rod anymore. And so what you want is to have this transfer function, but we know that this is limited, so we need also describing functions, and we use the work that was done here. And just to recall that the describing function gives you access to the whole thing here. You see, so you're able to actually compare the limit cycles with your calculations. While if you do linear analysis, you don't see all that. You see just the little part here. This is what you see with linear analysis. You see, this is what you see with nonlinear describing function analysis. It gives you much more information than what you have from the linear analysis. This is a big point. It's not just a trivial thing. And how do we do this describing function? It's the same. You have the loudspeaker. You measure the heat release fluctuation, the velocity fluctuation. You have the swirler, which can be placed like that. The photomultiplier is here. And this is what you get. You get this sort of functions. And so it's interesting to examine what happens at the maximum and minimum situations, because now you see that there is this interference between the two modes, the acoustic mode and the convective mode. And both of them will act on the flame, and you can suspect that it's this interference which can be constructive or destructive. And in fact, we came to know that other people had the same transfer function data. That was in a meeting in Vienna. We had a European combustion meeting, and we had a poster on our transfer functions. And people from Munich, Wolfgang Polifke, came in and said, you know, I have the same sort of measurements with this feature here. You see, this is his data. And you see that, so what they did was to change the position of their injector, their swirler, with respect to the exhaust. And by changing the position, you change the position of this thing. So this is definitely a sign that a convective mode is there, and depending on the distance, you can place this point at a different value. So you just by changing the distance, you change the phase, and you modify the position of this trough, of this minimum. So by talking with Wolfgang, I thought that there was something like that, and then we evaluated that using the theory of the actuator disk theory. So that was not available. Nobody had told me beforehand the vorticity wave has this value. This is in the paper and checked with what I've shown before. So this is the paper of Komarek and Polifke containing this data. So now the situation is that you have the acoustic wave, you have this swirler, axial fluctuations, azimuthal fluctuations, vortex roll-up comes in here and interacts with the flame. We've seen such a mechanism, produces heat release fluctuation. And here, the transverse velocity fluctuations are going to combine with these axial fluctuations to produce swirl number fluctuations. So here, you have something which modifies the swirl number. The swirl number is not fixed. It has a mean value, but it also fluctuates. And this will also produce heat release fluctuations because the flame will breathe in some way due to that. And so the transfer function or the describing function is the result of these two quantities here. So swirl number fluctuations, vortex roll-up of the flame sheet. And indeed, when you look at the velocity fluctuations in the axial direction and in the azimuthal direction, you measure them in the flame. This is in this paper. You definitely see that that you have the two components. This one is slightly smaller than that one. and you can also calculate the swirl number fluctuation. So in this case, you have a fairly strong swirl number fluctuation, and this is the case where the interference gives you a minimum. And then at 90 hertz, you have something like that. The fluctuation in swirl number is lower, and in this case, you have a maximum. So there are these two mechanisms. One is vortex roll-up and interaction with the flame, and the other one is the flame moving due to this breathing. At least this is our interpretation. And what you see here is actually the 60 hertz and 90 hertz positions of the flame. And you can see that in 90 hertz, you have very large changes in the flame area, while here, basically less. Well, like that, it's difficult to see. But in addition, you see, you can actually scale the level of fluctuation in watts per cubic meter. You see, you have 18, 10 to the 7 watts per cubic meter for these rather high values here. And so this gives a scale of this of the heat release, and you can actually use that to see if the calculations can do that. And this is what we've done with also the help of Laurent Giquel from CEFRC. So we use here a gridding of the upstream manifold, and the flame tube everything is gridded here. This is the time step is small. We use flame thickening. I'll explain that perhaps at one point. And so we calculate the full domain. In addition, you need to put an ambient atmosphere volume so that everything escapes the combustor here. And by doing that, these are calculations, these are measurements. The 90 hertz is pretty well represented, you see. The 60 hertz, perhaps somewhat less, but the features are there. The level of oscillation is well retrieved. You see, there are much stronger oscillations here in heat release than in heat release here. And the values, you see, like 2 to 10 to the 8 at the higher points. And here you had 1.8 e to the 8. So they match fairly well. It's not pure coincidence. There is something there. And so you reproduce numerically, this is in physics of fluids, you reproduce what you see experimentally here. This is after Abel transform and so on. It's not just a direct view. It's Abel transformed flame shapes. All right, perhaps we stop here. We have more on that tomorrow, but I think perhaps for a few questions, if you have any. Also, during the lunch hour, if you want to join me at the table, we can continue the discussion. It's always fun to speak about science, so don't hesitate to sit at one of the reserved tables. Yes. Well, 2 minutes for questions because it's 8 after 12, and so we have a few minutes. Yeah.
Okay, you saying that you treat the swirl as a linear component.
Yes.
So, is it really the case that the downstream fluctuation of U prime and A prime is linear with the upstream of the positive?
Yes, the remark is about the swirler acting as a linear component. You've noticed that it produces a vorticity wave which is linearly dependent on the acoustic wave amplitude. Now, the acoustic wave is not very large. It's at least at first you can consider that the swirler acts in a linear regime. This is at least, first of all, I didn't know what the level of this vorticity wave was. So it was something to obtain, and the best is to start by linear theory before you do any nonlinear. Then we checked that you get that even in a full calculation of a cascade impinged by an acoustic wave. You get something like that. Yeah.
I have difficulties to understand why the frequency of the convective wave is the same as the acoustic wave.
Yes. So in the linear regime, you cannot have a different frequency. Nothing. It would be a mismatch between the time dependence. So you set in something which is at a given frequency, and you get. You see, this room, for example, is a linear object. I give a frequency here, you get the same frequency at.
Experimental data that you showed were in agreement with it.
Now, yes, in the experiment, you've seen that the signals are nonlinear because combustion is highly nonlinear. In the purely acoustic, for example, in the calculations, in the calculations of the cascade, here you see the signals are really sinusoidal. They are very sinusoidal. So in that case, now we didn't go to very high values of. We could have done that. Yeah, it's. So basically, much of the acoustics is in the linear regime. The swirler operates in the linear regime, but the flame is nonlinear and produces signals which are nonlinear. You see when you look at the signals at the flame, they are like that. So they are somewhat sinusoidal. Here, not so much. So you have higher order, higher harmonics, because the flame is like that. It's you see the swirl number fluctuation is not quite, has a weird shape, but periodic. Any other question? Yes?
Did you consider trying to make a transfer function between these two different fluctuations and also the transfer function between those oscillations separately in the flame?
So no, we haven't done that. We study. You see the the paper actually it's called the combined dynamics of swirler and flame. So we treated the whole thing all at once. So we lose some of these differences in doing that. So yes, could be done. But then you need to put transducers on the downstream side of the swirler, on the upstream side, to get just the two components. And then sometimes you can believe in theory because it's checked by numerical work, it is checked by experiments. The agreement is very good. The level of the amplitude level is good. The convective velocity is there. So you basically have the components. So you could actually express that in terms of separate transfer functions as well. In this case, we said, well, what we know is the acoustic wave coming in, and the system is treated, including the swirler. Yeah. But the separation between the two could be done. I think it's a good idea. Yeah. All right, so it's time to stop. Thank you for this, and we'll see.